Okay, good afternoon. So let's start the class. So today we will, let me see. So today we will talk about some examples of the application of pigeonhole principle. So let me briefly review what it is. So this is the general form of a pigeonhole principle. We assume that there are k boxes and then there are going to be n balls. These n balls is going to be distributed into these k boxes. So none of the balls will be left outside. So we want so pigeonhole principle says that in any scenario of the distribution, there must be some box, at least one box, okay? And then inside that box, it contains at least so many balls. So the number here is determined by the average n over k, taking the ceiling. Is that okay? So if there are 5 balls and 2 boxes, then one of them will have 3 or more. If there are 17 boxes, and then let's say there are 100 balls, then one of them will have 6. Is that, no, 7. 115, did I mention 15? Or let's say 15. 100 balls, 15 boxes, then one of them will have 7 or more balls. Is that okay? So because 100 divided by 15 is like 6 point something. And then if we take the ceiling, then it becomes 7. Okay, so this is the general version of the pigeonhole principle. And let's see some application. So the first example here is perhaps the most famous one. So it says that, so when we have 6 people, so let's say 1, 2, 3, 4, 5, 6, okay. And then between these people, let's say they can be friends. So if they are friends, I'm going to use orange to join them. So they may be friends of each other, or they may be enemies. So let's say if they are enemies, I'm going to use dotted line. So these are enemies. So between any pair of them, they must either be friends or enemies. So let me join them. Okay. So maybe I'm going to join these two. Let me see. 1, 2, 3, 4, 5, 6. 1, 2, 3. Let's say I'm going to join them. 1, 2, 3. Let's say I'm going to join them by a dotted line. Okay. So this is a particular case. Then we must be able to find 3 mutual friends or 3 mutual enemies. So mutual friends are forming a triangle with solid line, and then mutual enemies are forming a triangle with dotted line. So we are not saying that we will be able to find a triangle of solid lines and a triangle of dotted lines at the same time. We are claiming that either this one or this one must occur. Okay? So let's see this example. Do we find a solid triangle? Maybe not. So we don't see a solid triangle. But on the other hand, so there is at least one dotted triangle. If you pick this vertex, and this vertex, so the lines between them, so this one, A, B, and C. Let's say A, B, C. If you pick A, B, C, then they are joined by dotted lines. Is that okay? So this example, this is a particular case. But if we want to mention that in any scenario, no matter how you draw the lines, actually you can think of this as a coloring problem. We are coloring the edges of a complete graph of 6 vertices. So we are using 2 colors, either the solid color or the dotted color. And then we want to say that no matter how you color the edges, there must either be a solid triangle or a dotted triangle. Is that okay? Now, let's take a look, okay, for a slightly different case. How about 5? How about 5 vertices? So let's say we have 5 vertices, and then we are going to make a complete graph of them. And then each edge we can color either solid or dotted. Is it always possible? Is it always? Is it guaranteed that we must be able to find a solid triangle or a dotted triangle? So I want to ask, is it possible that after the coloring we cannot find any solid triangle and we cannot find any dotted triangle? Is it possible for 5 vertices? Yes, for 5 vertices, yes. This is one example. So this is solid, is that okay? And then all the remaining, they are dotted. So if it is 5, so for 5 vertex case, so I call this a complete graph, K5. We call it a complete graph with 5 vertices. K5, there is no guarantee to see a solid triangle or a dotted triangle. Is that okay? Of course, you can in some case you will see solid triangle. If you color all of them solids, then you see solid triangle. But there is no guarantee that you will always see solid triangles or dotted triangle. But on the other hand, what we are going to show, so in K6, so we are guaranteed, so this is what we want to show. So we are guaranteed to see what? To see a solid triangle or a dotted triangle. Okay, so for instance, if we color all of them solid, then of course we can see solid triangle. And here, this is another case. We try to color them in certain way, and then we will see a dotted triangle here. And we want to show that no matter how you color, then you will always see one of them. Of course, or both, okay? Okay, let's show how, let's prove it. So the proof is like this. So there are 6 vertices, right? So let's pick one of them as our main character. So this is U. So this is U. Okay? And then, so there are going to be 5 other vertices outside, right? Okay? You are going to form a relationship with these 5 people. But there are 2 types of relationship. Either you are going to be friend or you are going to be enemy. Okay? So what does it mean? That means that, okay, you may either get 3 or more friends or 3 or more enemies. Think of this as color. So one type of color will appear 3 or more times. Does that make sense? So this is the pigeonhole principle because there are going to be 5 relationships you are going to make, but then there are only 2 types. Okay, so that means that out of these 5 relationships, one of the type must appear 3 times. Is that okay? I don't know which one, but let's say a certain one. Maybe dotted, maybe solid, I don't know. So let's call it curvy line. Okay, so okay. So I'm using curvy to represent the relationship that appears more frequent. Is that okay? Now, what will happen? Okay, if these 2 persons are joined by the same curvy relationship, then you have a triangle of the same color. Does that make sense? So we are going to look at these 3. Let's call it A, let's call it B, let's call it C. So if A, B are joined by curvy, then you get a curvy triangle. If AC is joined by curvy, you get a curvy triangle. If CB is joined by curvy, you get a curvy triangle. And if you don't want to get a curvy triangle, then what will happen? Then in that case, then AB must be joined by the other type. AC must be joined by the other type, opposite of this curvy. And then CB must also be joined by the other type, opposite to the curvy. Okay? So in that sense, we will see the other type of a triangle appearing. Okay? So that means that you cannot avoid. Okay, no matter how you color the edges of a K6, of a complete graph with 6 vertices, then either you will have a solid triangle or you have a dotted triangle. If you are okay with this, could you please raise your hand? Okay. How about 7? K7. So if I have a K7, I want to color all the edges in 2 colors, then what will happen? Then again, you must always have a solid triangle or a dotted triangle. Yeah, because K7 contains more edges, right? You can just ignore one of the vertices, take it out. If you don't consider that vertex, you will already see a solid triangle or curvy triangle already, right? So K7 must guarantee. Okay? So this problem is belonging to a branch of mathematics called Ramsey theory. So basically, we want to find out what is the minimum number of minimum size structure that you want to look at so that it guarantees something to happen. So here, the structure that we are looking at are complete graphs. So what is the minimum size complete graph that guarantees if the edges are colored in 2 colors, a triangle of the same color will appear. Okay? So you can extend this problem like, okay, so let's say, what is the minimum size of a complete graph such that if we color the edges in one of the 3 colors, let's say you can color in red, orange, or black, okay, that you will guarantee a red triangle or an orange triangle or a black triangle to form. Does that make sense? So this will be another type of problem. Or you can ask for more complicated objects rather than triangle. Maybe like, what is the minimum size of a complete graph such that you color the edges in 2 colors. And then you will find a complete graph of a solid triangle or a dotted K4. So you will find 3 mutual friends or 4 mutual enemies. So you can ask problems like this, okay? Okay? Okay. Okay, so if you are interested, then you can go to the web and search for this keyword, Ramsey theory. Okay? Good. Okay, now another exercise, the other exercise. Okay, exercise, let me call it 2. Okay, so let's say I have a sequence of 1s and 0s, 1s before 0, so 1, 1, 0, 0, 0, okay. So this is like 11,000. This represents the number 11,000. Is that okay? And then, for instance, this one is 1,110. Okay? And let's say this number is just 11. Is that okay? Now we are going to look at numbers of this form. The first part are 1s, and the latter part are 0s. Okay? And then it must start with 1, okay? But you may not have any 0s. Is that okay? Now, so there are many numbers of this form. And then we want to show what? We want to show that one of these numbers, so there exists a number of this form such that, so we want to show that there exists a number of this form. So let's say there are j of them, and there are k of them, such that it is divisible by okay, let's say by 2017. So next year is 2017. Okay. Or maybe if you like 2016, maybe. Yeah, let's try 2016. So how can we show? Everyone understand this question, right? So for instance, if I change it to 4, okay, so there exists a number of this form such that it is divisible by 4, then you can think of the number like 100. 100 is divisible by 4, okay? If you want to change it to 7, something like 7, then what will happen? 7, let's try, okay? So 7, let's try 1. So 1 is not divisible by 7. Let's try 11. No? 1, 1, 1. Okay, so let's use the long division method, okay? So let's see how many ones do we need, okay? So if it is a 7 here, 7 times 1 is equal to 7, you have 41, am I correct? And then 7 times 5 is equal to 35. Okay, still not okay. So let's have another one. So it is 61. Is that okay? So 7 times 8, 56. So you have 5. Still not okay. Let's have a 1. So 7 times 7 is equal to 49. Is that okay? So the remainder is 2. Okay, so if I have a 1 here, then it is like this. So finally, we find a number 111, 111, and then it is divisible by 7. Okay. So how about this one? So how do we show that there exists a number of certain form? Okay, of course, you don't want to have just a 0. 0 is divisible by 2016. So that's why I restrict the j part to be at least, there is at least 1 1 there. So it is a non-zero number. Okay. Hint. Okay, so this is my hint. Let's say x is a number. If you divide it by k, let's say x, you divide it by k, and then you get a modulo k as a remainder. And let's say this turns out that if you try to divide another number y by k, and you get the same remainder. Okay, so x mod k is equal to y mod k. Let's say we have this one. So what is so special about this x minus y? What will happen to x minus y? So this is the key idea. So if I have two numbers, let's say 17 and then 26, okay. If they divide by 3, 17, you divide it by 3, then you get a remainder 2. Is that okay? 26, you divide it by 3, then the remainder is also 2. Then the difference between them, 17 and 26, it is equal to 9, right? But then 9 is always divisible by 3, right? So here, we have this observation. If we have two numbers, and they, after dividing by the same number, they have the same remainder, then the difference must be a multiple of, so this is going to be a multiple of k for some c. Does that make sense? Is that okay? Okay? Yeah, the reason is simple, because x is equal to a certain k, c1 k plus some remainder r, and then you say that y has the same remainder, so it is equal to c2 times k plus the same remainder. Am I correct? So if you take the difference, x minus y, then this will be equal to c1 minus c2 times k. The remainder is gone. So that's why the difference is always a multiple of k. Okay, so this is the hint. So what shall we do? What shall we do? Okay, so let's look at the numbers. 1, okay, and the number 11, and the number 111, and so on and so forth. Let's say we look at many numbers. 111, 111, 1. Okay, let's say we are going to look at how many of them. Let's say we are going to look at 2017 of them. So many numbers. Okay? And then we try to divide them, each of them by 2016. 2016. And then we want to divide them by 2016 and get the remainder. What will happen? What will happen? Good. Some of them will be the same, right? Yeah, because how many remainders we are going to look at? We are going to look at 2017 remainders. But then the remainder, when you divide it by 2016, there are only 2016 types of remainder, right? So some two of them will be the same. Some two of them, maybe 1111 will be the same as 1111. Am I correct? Is that okay? So they have the same remainder. Let's say they are, this is of length I, this is of length F, whatever. Okay, let's call it G. Then what will happen? Then the difference of them will be a multiple of 2016. So what is the difference? The difference will be of this form, 1111 and then 0000. Is that okay? So they are going to be, well, if G is longer, then they are going to be F zeros and they are going to be G minus F ones. Is that okay? Does that make sense? Yeah? And then this is a multiple of 2016. If you are okay with this, could you please raise your hand? Okay, good. So this is how we show this. Okay? Now, if we change the question a little bit, this time let's make it 2017. Okay? Then the problem changes, but we can use the same technique to show that there exists a number of this form divisible by 2017. What's more is that because 2017 is not divisible by 2, not divisible by 5, okay, so if you say that this number is a multiple of 2017, then you can divide this number by 2 and divide this number by 5. It doesn't matter. The number will still be a multiple of 2017. Is that okay? So we can make the argument a little bit stronger. So if it is like 2017, we can show that there exists a number of this form. It consists of only ones, and then it is divisible by 2017. Is that okay? Whenever this number is not divisible by 2 or 5, okay, so why we can claim something like this? So first of all, this is correct, right? This is correct. We use the same technique. So that means what? That means we can find some number of this form 1111 and then 000. And it is a multiple of 2017. Is that okay? Now, we need some theorem we will show later, but you know, every number has a unique prime factorization. Okay? So this number, if in terms of prime factorization, you can write it down as the prime factorization of the one part plus 10 to the power, let's say this is small k of them, plus 10 to the power k. So this number looks like this form. Am I correct? And then 10 to the power k, you can write it down as 2 to the power k and 5 to the power k. Is that okay? Is that okay? And then if 2017k is equal to this one, then that means that we can divide it by 2 to the power k. This part is still an integer. Is that okay? But then if you divide this by 2 to the power k and then it is still an integer, then this 2 to the power k must be absorbed inside this big K part, because you have no common factor between 2 and 2017. So after dividing by 2 to the power k, what will happen is that, so if we remove So let's say this is 2 to, so we can write 2017 big K is equal to this one. So if I divide both sides by 2 to the power K, then what will I get? I will get this K becomes a smaller number. Let's call it K prime. Is that okay? And moreover, if I further divide this by 5 to the power K, then I will make this even smaller to a K double prime. And there is no effect on this 2017 because it has no common factor with 5. So what do we get? We get 2017 K double prime is equal to 111. So 111 is a multiple of 2017. And that's it. So we can make this stronger. If this number does not have a 2 or 5 as a factor, then we can strengthen this result by removing the 0 parts. Okay? That's it. Okay, good.